Hey everyone, I know it's been a while. A long while actually. But I wasn't being lazy, just had a little too much going on. First of all, I want to say a huge thank you for all the support I received on my last laser projector video. I still can't believe we passed 6,000 subscribers, so seriously guys, you're awesome. I know that in the last video I mentioned I want to make a laser projector without using stepper motors, and that's still the case. But in the meantime, I decided to work on something that can be used by all laser enthusiasts. So today, I want to show you my new laser deck board called ILDA Wave X16. So let's get started. First, let's quickly go over some basic theory about laser projectors. And no, I don't mean the ones used to watch movies. Those are only called like that because they use laser as an upgraded light source instead of the lamps or LEDs. I'm also not talking about those laser party lights that split the beam into different shapes using diffraction gratings. I'm referring to laser scanning projectors where the laser beam is steered around to draw vector graphics. Different projectors might use different designs, but the core principle stays the same. A typical setup consists of a laser diode and two mirrors mounted at a 90-degree angle from each other. One mirror moves the beam left and right, and the other moves it up and down. It's important to be able to move the mirrors with precision, but also fast enough for the persistence of vision to do its job, so the image looks stable instead of just a flickering dot. This concept of moving the laser beam is known as a laser beam steering. Nowadays there are many different technologies that can do it, such as piezoelectric microgimbals or MEMS mirrors, and these are used across various industries. But when it comes to laser show projectors, the most common solution is still a specific type of actuator called a galvanometer, or galvo for short. I explained how they work in my last video, so if you're interested, I'll leave a link in the description. Both the galvos and the laser diode require dedicated driver circuits which take in control signals, in case of galvos also position feedback, and use that to regulate the output current with high speed and precision. To control everything, there's usually a microcontroller, which is basically the brain of the projector, generating the control signals and sending them to the drivers. It looks something like this. These are the laser diodes and their driver. In this case we have red, green and blue laser mixing using dichroic mirrors to achieve multiple colors. These are the galvanometers connected to their driver board. And this is the main board with the microcontroller. We also have one more module which takes AC wall power and generates required voltages for the other boards. So we covered the basic components, but now this raises two important questions. How does the MCU communicate with the drivers and how does it know what to project? Well, some projectors come with firmware that already includes a bunch of built-in presets. In some cases there's even a microphone on board so the visuals can react to music. But what if we want to control it ourselves? This is where ILDA comes in. ILDA stands for the International Laser Display Association, and they've defined a standard protocol to make sure projectors, software, and controllers from different manufacturers can all work together. One of the key parts of this standard is the ILDA image data transfer format. It's a coordinate-based file format that tells the projector where to move the beam, what color to choose, and when to turn the laser on or off. It works by defining frames, which are sets of points that make up a single pattern, and these frames are arranged in a sequence, so when they are played at a specific scan rate, it results in an animation. That's why many projectors include an SD card reader and implement logic to parse and interpret these files, so you can design your animations on a computer, save them to a file, and run them directly on the projector. But now, what if you want to go beyond that and control the projector in real time? For that, there are two main protocols used. The first is DMX512 or simply DMX, which you've probably seen in stage lighting setups. It's what controls moving heads, fog machines, color changers, and so on. You can recognize it by the 3 or 5-pin XLR connectors. DMX is great for triggering effects or switching between patterns already stored on the projector, but it's a slow-speed protocol, not fast enough to send real-time coordinate data. That's where the ILDA standard projector or ISP interface, also known as ISP-DB25, enters the game. It is a set of analog voltages that can directly control the projectors in real time. Among others, it includes X and Y channels, both expecting 10V peak-to-peak differential bipolar signal, and RGB channels for color, which use 0 to 5V unipolar signals. This standard uses a DB25 connector. Yes, it's the same one used on old-school parallel printer ports. It also makes sense since this standard dates back to 1996. Nowadays, modern laser projectors are starting to adopt newer technologies. For example, some have Ethernet ports that allow to use updated versions of these older protocols like RNet or SACN, which brings DMX over Ethernet, or another ILDA standard from 2015 called IDN, which can actually stream laser frames in real time over the network. Now let's move on to the second question. How does the microcontroller communicate with the drivers? This part is a bit trickier because different manufacturers can use different approaches. If you've ever considered building your own projector, you've probably come across galvo and laser kits like these. They include their own driver modules along with specs for the control signals they need. You'll often find these modular drivers in lower cost or generic projectors, while big name brands design their own circuits to increase quality, add more features like protection, but also to save space and improve efficiency. These galvo drivers normally follow the ILDA standard, so they expect a differential analog signal in the range of +- 10 volts. If you provide -10 volts, the galvo moves fully to one side, +10 volts moves it to the other limit, and all values in between are translated linearly. Most of these drivers still operate using classic analog circuitry, which is a closed-loop servo amplifier. It's an old approach that works well, doesn't suffer from latency issues, and is still widely used even by big brands, except for a few pioneering companies that are transitioning to DSP solutions. As for the laser drivers, they typically expect a unipolar analog control signal in the 0 to 5 volt range, which again coincides with the ILDA standard, but this can vary depending on the driver design and the IC it uses. For example, this particular driver uses a PT4115, which is an adjustable current driver where the input signals up to 0.3 volts are treated as off. The dimming range is roughly linear between 0.5 to 2.5 volts, but it can also accept the PWM signal. But how do we output all these analog voltages if the microcontroller only works in a digital domain? This is usually handled in two steps. First, we use a digital to analog converter, or DAC, to generate the analog voltage. This output is always positive and normally not higher than the microcontroller supply voltage, so 0 to 3.3 volts. Then in the second stage we use operational amplifiers to amplify that signal and shift it into a bipolar range like +- 10 volts. If we want to simplify choosing a suitable DAC, there are two main parameters to consider: resolution and speed. Resolution determines how many distinct voltage levels the DAC can produce. Let's say we want to generate a sine wave. A perfect sine wave is a continuous function, which means you can zoom in infinitely and still see smooth transitions between values. But since we are working in a digital system, the wave will always be quantized into discrete steps the DAC can output, and the number of available steps is dictated by its resolution. For example, an 8-bit DAC can output 2 to the power of 8 or 256 levels, a 10-bit DAC gives you 1024 levels, and a 16-bit DAC offers 65,536 discrete levels. The higher the resolution, the more finely we can represent analog signals, which means smoother curves and better image detail. Since the galvo drivers are analog, they can handle continuous signals, so your DAC resolution becomes the limiting factor in terms of precision, at least in theory. Of course, past a certain point, the resolution becomes indistinguishable due to analog noise and imperfections, but that's the basic idea. Speed is the second factor. We need to update the DAC output quickly enough for smooth motion, especially because we are moving mirrors in real time. That means both the communication speed with the DAC and its internal conversion speed must be high. For that reason, high-speed DACs with an SPI interface are preferred, as they are fast, simple to implement, and easy to synchronize. Some microcontrollers already have built-in DACs, but they are usually limited in either resolution or the number of available output channels. So for applications like these, external DAC chips are preferred. That said, the only reason why we even need this digital to analog conversion is because analog galvo drivers are still so common. It's just easier to build around them than to design a whole new system from scratch. But as I mentioned earlier, there are already a few companies developing drivers where the control logic is digital, and I think we'll see more of that in the future. So now that we've covered the basic principles of how everything works, where do we even start if we want to make our own laser show controlled from a computer? Well, it really depends on what hardware you have available and what kind of budget you're working with. If you're doing this professionally, or you're a serious hobbyist with some money to spend, you'll probably go for a high-end laser projector that includes an ILDA socket, or maybe even one of the newer models that support the network-based protocols. If you only have the ILDA socket available, you need a laser DAC, which is a device that connects to your computer, performs the necessary digital to analog conversions, and outputs ILDA signals directly into your projector. There are quite a few laser DACs out there, and their prices vary a lot. On the high end, you've got industry standard units that only work with proprietary software and can cost hundreds or sometimes even thousands of dollars. Then there are more budget-friendly options with open source support. They are definitely more accessible for a regular user, but they can still cost around $100 to $300, and the cheaper ones often lack networking features, so you can only use them through USB. But what if you've got a cheap projector without an ILDA input? Or if you want to build your own projector from scratch using individual laser and galvo driver kits? In that case, your options are limited. If we simplify it, laser projectors generally fall into three categories: professional systems, which are powerful, feature-rich, but expensive; mid-range systems, which are more affordable, but still not exactly hobbyist-friendly. Even though you can find exceptional products that offer wireless control and user-friendly platforms, they are still proprietary and difficult to expand or modify. And budget projectors, including home builds, which are cheap, but can be easily controlled without some sort of hacking. Fun fact, some people actually modified the DAC in their sound card to generate the driving signals. So I've decided to make my own laser DAC that bridges the gap between these options. It's open source and supports both the standard ILDA DB25 output as well as an individual pin headers to directly wire into driver modules. Think of it like the Arduino of laser DACs, which is a low barrier, flexible platform, allowing enthusiasts to get hands-on experience without a lot of overhead. It runs off 5 volts via USB-C, which can also be used for data transfer, and the board generates the bipolar voltages required for ILDA signals. Or if you're integrating it into an existing projector, you can also power it from an external power supply up to ±15 volts. It features an 8-channel 16-bit DAC and all outputs are properly conditioned to match ILDA specifications. There's also a micro SD card slot, so it can load and play ILDA files directly, and is Wi-Fi enabled so you can control your projector wirelessly. It runs on the Arduino platform, making the code easy to understand, modify and expand. Whether you want to write your own firmware, experiment with real-time control, or just learn how everything works. I'll get into the firmware later, but for now, let's take a look at the hardware design. The brain of the board is an ESP32 S3 module, a powerful dual-core microcontroller running at 240 MHz. It comes packed with native USB, Wi-Fi and Bluetooth support, making it perfect for real-time communication and wireless control. The ESP interfaces with 2 user buttons, addressable RGB LED, and the micro SD card socket with ESD protection and EMI filter. The board is powered through a USB-C connector which handles both the data and power input. The USB data lines are protected by dedicated ESD diodes, and the power line is routed through a 500 mA fuse and filtering components before entering the power stage. I'm using a TLV61048 boost converter to generate a ±8 volts relative to ground. Since USB input can drop as low as 4.5 volts, I need to ensure a stable 5 volts plus some headroom for the op-amps, and boosting to 8 volts guarantees consistent performance even under lower USB supply conditions. These 2 voltages are routed through a diode O-ring circuit, which also takes input from the optional external power supply. This setup allows the board to switch between USB and external power supply while preventing backfeeding. So even if it's installed in a projector with its own power supply, you can still safely connect the USB cable for programming or debugging. After the O-ring stage, we get VDD and VSS, which are the positive and negative rails for the analog circuitry. VDD is also branched off and stepped down to a stable 5V rail, which is then further regulated to 3.3 volts using an LDO. The 5V rail powers the DAC, LED and is also used for the binary ILDA signals, while the 3.3V rail supplies the rest of the digital circuits including the ESP itself. Now for the ILDA connector, let's first take a closer look at the official documentation. We can divide the ILDA signals into 2 groups: required signals, which must be implemented for proper operation, and optional signals, which some projectors support, but not all of them. The required signals are X and Y for beam position, R, G and B for the color channels, shutter for laser blanking, ground, and interlock loop for safety. The optional signals are intensity, used for global brightness control, projector return, a feedback line for monitoring, and few user-defined channels that can be repurposed for custom functionality depending on the setup. The interlock is simply a safety feature, 2 pins that must be electrically connected to each other. The projector checks this loop, and if it's ever broken, it will immediately shut off the laser. On my board, this is handled passively by tying the 2 pins together with a PCB trace. Almost all of the signals, except for the shutter and projector return, are specified as differential pairs. That means each signal has a positive and negative line carrying equal and opposite voltages. This differential signaling is used for noise immunity, especially when running long cables. The same principle used in balanced audio through XLR. Since external noise affects both lines the same way, the receiver can simply subtract one from the other and cancel out the interference. The X and Y signals should be bipolar 10V peak to peak, meaning they swing from -5 to +5 volts. To generate the signals, I'm using the DAC 8508 from Texas Instruments, which communicates via SPI. It has a 2.5V internal precision reference, and I'm running it with a gain 2 configuration, resulting in an output range of 0 to 5 volts. For the X and Y axes, the outputs are processed through a 2-stage op-amp circuit. The first stage is a differential amplifier with a gain of 2, which subtracts the reference voltage from the DAC output and doubles it, effectively converting the 0 to 5V range into a bipolar -5 to +5V signal, which becomes the ILDA compliant positive output. That same signal is then fed into a second stage, which is a unity gain inverter that simply flips the polarity, generating the corresponding negative output. The RGB, intensity, and user-defined signals are all specified as unipolar 5V peak to peak. In a differential configuration, this would typically mean +2.5V on one line and -2.5V on the inverted line. However, for simplicity, I chose to reference these signals to ground and drive them directly using the DAC's 0 to 5V outputs. The DAC has 8 channels and I've used all of them, leaving out the 2 optional user-defined signals. All outputs are also terminated with 150 ohm resistors, as specified in the standard. This helps with current limiting in the event of accidental shorts and also provides impedance matching to reduce signal reflections and ringing over longer cables. The shutter signal is already defined in the standard as ground referenced, so in this case I implemented it as a binary on-off signal using a MOSFET as a low side switch. For the PCB layout, I went with a compact rectangular design that can later fit into a plastic enclosure while still providing easy access to all necessary ports and the SD card slot. If we connect an oscilloscope to the X and Y output channels of the board, we can observe the generated waveforms. But the real magic happens when we switch it to XY mode. In fact, an old CRT oscilloscope in XY mode is the perfect analogy for how laser scanning projectors work. In both cases a beam, in this case an electron beam generated by a cathode ray tube, or the laser beam in the projector, is deflected horizontally and vertically by the analog voltages. So the path the electron beam takes on the oscilloscope screen is the same path the laser beam would trace to create an image. Regarding the firmware, I'll be honest, it's not fully finished yet. Right now it's just a proof of concept, something to build on later. But I still wanted to show you how it's structured. If you want to play with it yourself, the full source code is on my GitHub. So first we have a library for the DAC that initializes it and lets us write into individual channels. We can then trigger all of them at once, which is important for keeping everything in sync. Next is the SD card library that mounts the card and read files from it. The renderer is the heart of everything. It has a ring buffer of points, each one having X, Y, RG and B values, and a timer that periodically takes the points from the buffer and sends them to the DAC at a specified scan rate. The buffer is shared so we can add the points from different sources. For example, we have a thread that parses ILDA files from an SD card and add the points to be displayed. The ILDA parser is defined in a separate file, and I must give a huge shout out to Chris from Atomic 14 who also wrote an ILDA parser for his board, which was a great starting point. He works on a lot of amazing stuff, so make sure to check his channel. I've made the parser to load the contents of the file in chunks. This way, not everything is loaded into RAM at once, so we can play even large ILDA files. Since the ESP has Wi-Fi, we can also do network control. I wrote the basic IDN parser, which reads the UDP packets, extracts the relevant data according to the standard, and adds them to the buffer. The protocol also defines a packet format called IDN Hello, which allows software to automatically find compatible devices on the network. I tested this with a free program called LaserShowGen that worked pretty well. Next, I defined my own lightweight protocol called IWP or ILDA Wave Protocol, together with a Python script that can be used as a sender. It's super simple, no handshakes, no error checking, which means it can run really fast. Finally, there's a tiny web server that lists the SD card contents, lets you adjust brightness and scan speed, and change the Wi-Fi password without reprogramming the firmware. I'm linking my website where you can find all available information with links, so feel free to check it out for updated information, and of course, don't hesitate to leave a comment if you have questions or suggestions. I always love hearing from you. Thank you for watching and I'll see you next time.